Hello, welcome back. Now, in some of the previous videos, you've started to learn about treatment planning, some of the concepts behind that. In this video, I'm going to introduce a couple of concepts, terminology, that we use when we're talking about treatment planning. And we need to have a language to communicate about planning, and so this is an important part of that. So we're going to talk about definitions for different volumes that are used for treatment plans. And we're going to talk about how dose distributions are quantified in terms of the DVH and other parameters. So this will form a very important basis for communications around treatment plans, and it's going to help us understand what comes next in the later videos. So here we go. In these videos, I'm going to be making reference to these reports by the ICRU, these recommendations. So ICRU is International Commission on Radiation Units and Measurement, and in these reports, they're providing guidance on prescribing, recording, and reporting dose. So there are three main reports spanning the decades, the most recent one being 83 from 2005. They define and describe several structures that are important. This aids in the treatment planning process, and it provides a comparison for a basis for comparing treatment outcomes. So it's the standards for these type of things. And here are the definitions. So you've got the gross tumor volume, the GTV. And so that's something that you can palpate or something that you can see radiographically on imaging. It's expanded into a clinical target volume, a CTV. And that typically accounts for the spread of occult disease that you can't see on imaging. Then there's an internal target volume that accounts for motion of the tumor, physiological and other effects. And then finally, there's a planning target volume, a PTV. So that accounts for the setup uncertainties and kind of a margin to make sure you treat the intended target. And then there's a treated volume, TV, treated volume, and that's kind of the dose that's treated. And then there's the irradiated volume, which the ICRU defines as the largest volume that receives a substantial dose that they define. So let's look at treated volume. Treated volume is the volume enclosed by an isodose surface, and it's specified by the oncologist as appropriate to achieve the purpose of treatment. So here's an example. So you're treating a prostate and you're treating the seminal vesicles, and here's the PTV, and the treated volume is larger than that volume. So it's the volume enclosed by that surface. And the irradiated volume is a little bit larger. That receives a dose that's considered significant in relation to normal tissue tolerance. Usually that's taken to be the volume enclosed by the 50% isodose curve by convention. So let's look at a case study now. This is a patient with head and neck cancer, and they're receiving treatment to a GTV, the primary disease, and then a GTV for the nodes, the nodal volume that has a tumor, and then those are combined in one GTV and then expanded into a CTV, a clinical target volume that extends out here in orange. And then around that is a further expansion out to the PTV, planning target volume. Okay, so there are other volumes as well. So we can look at an OAR, organ at risk. So here you see over here the parotid gland, and then also at the spinal cord. These OARs are, the serial ones at least, are often expanded into something shown here. And this is PRV, planning risk volume. So the expansion here accounts, again, for setup uncertainties and so on. So as the patient moves or as the anatomy moves, the OAR will still be in this PRV envelope. So it gives us sort of a buffer, a conservative way of handling the dose to that critical structure. One special note here, in ICRU 83, they talk about tubular OARs, organ at risk. So an example is the rectum. So the tubular organs shouldn't include the inner contents, they say. We should look at the wall. But in practice, you do optimization of the IMRT that we'll talk about in future videos. You do it with the full OAR, but then evaluate the DVH for the lumen wall. And this should make sense more as we go on. So now I'd like to say a little bit more about nomenclature and standards beyond what's in ICRU 83. So coming back to this example, if we look at just at the OER for the cord, it could be named as cord. It could be named as spinal cord. It could be named as spinal cord with an underscore. The different capitalizations, different spellings. If you have laterality, it could be, right eye or RI or I right. So there are many possibilities for naming, and we need to standardize this in order to be able to communicate about it, in order to be able to run trials and to collect data. So there's a new standard out, and that is published in 2018, which is the AAPM Task Group 263. And this tries to bring a rational basis to this and provide recommendations, especially for the naming of structures and the reporting of dose metrics. So this is the work of many, many people over quite a few years, so I want to give credit to them. This is the table from TG263, just an example of it. So here you'll see left lung, and here's how it should be named according to this report. And then here's another example, right lung, and then you can see on this list further down lungs, and it explains how those should be combined, and then you could have lungs minus PTV, and that's a logical operation where you take the lungs and you algebraically subtract out the PTV from there. So this and the rest of the table provide standards for naming that allow us to communicate. Now we're going to go back and look at this expansion, GTV, CTV to PTV, again, and try to understand it more rationally in terms of what margin is appropriate. So as we said before, the expansion from gross target volume to clinical target volume accounts for the extent of disease that's not necessarily observable radiographically. Then the expansion from CTV to PTV, planning target volume, that's to account for variability in basically targeting of the beam relative to the patient. So that expansion we can understand, and we can start to ask the question, what is the appropriate margin for that expansion? So to understand that, we're going to have to talk about the variability in patient alignment and setup during treatment. So let's look at that. I'm going to start here with a little X, and that's the intended target of position of the beam in the patient. And now let's start treating. So let's look at day one. So here's the position of the treatment on day one. And then here again, day two, day three, day four, and so on. So every one of these points is the location of the treatment on a particular day. And you're trying to align to the X, but it's not a perfect process. There is some variability. So what I've shown here is the process of random error, which is given the symbol sigma, little Greek letter sigma. Let me explain the symbol and where it comes from. It comes from the distribution of points in space. And you'll remember this probability distribution. I can draw it here. The number versus some value, say the position, and it follows some bell-shaped curve. That's the Gaussian probability distribution with some width. And here's the formula for this. You don't have to remember this, but just to show you. But the key thing here is that it has some width, sigma, some standard deviation. That says how wide the distribution is in space. So let me just plot another one here just as an example. Maybe this one is a little wider. Maybe for whatever reason the random error in this process is a little larger. Maybe you don't have image guidance or something. Okay, now let's consider another setup down here, and I'm going to do the same experiment with a different treatment, say a different patient, different process, and here day by day, and you'll see the points are starting to align center around a point that's not centered on the X. So this is called systematic error, and it's given the Greek letter capital sigma. So there's this offset of the average position with the intended position. So systematic error has a very important effect and a big impact on the treatment. So now with the understanding of these type of errors, we can go and start to look at what is the appropriate margin for expansion in order to cover the planning target volume. So people have used these values to come up with some recipes for margins, and this is a summary from ICRU 83. Different authors have come up with different formalisms. This author says you should use some multiplicative factor of the random error. Another author says, well, no, you need to include the systematic error in addition to the random error, and they have different effects. You'll often see this one quoted, the Van Herk et al. Margins, and it's one of these formalisms. And one of the key things here in any of these formalisms is that the systematic error has a much bigger effect than the random error because it shows up every day, right? Okay, so that's the summary of that. If you can measure the big sigma and little sigma, which you can in theory, then you could come up with this formula for defining the appropriate margin for your population of patients. All right, so now we're going to address this question of how to prescribe and specify dose. And that might seem like a very easy problem. Say I want to give a tumor 45 gray. Let's do it. But as you think about it and dig into it, it's actually not that simple and it needs some codification. So one standard for this is published in 2016, a paper from ASTRA, the American Society for Radiation Oncology. And they came up with a standardized way to prescribe dose. And a very simple, the simplest form of this is that you want to specify the treatment site, the delivery method, the dose per fraction, the number of fractions, and the total dose. And then all those together should give you the prescription. So for an example, I might prescribe to the left lung, delivered through photon treatment, 200 centigrade times 32 fractions for a total of 6,400 centigrade. And they're advocating here that you specify the units in centigrade because it avoids the issues of decimal points. Incidentally, also related to this, the Society is advocating for a minimum data element set that should go with a treatment prescription. And that includes the dose, but other things as well. So let me just mention it here. So here are the minimum data elements listed: diagnosis, treatment site, we just saw, dose per fraction, modality, treatment technique, number of fractions planned, number of fractions delivered, total dose planned, total dose delivered, and then the start and end date of treatment. So let me come back again to the question of how to prescribe and specify dose, because even with the standards I just showed you, it's still not quite that simple. So I'm going to make reference to the ICRU Report 83 and discuss how we define dose. So one method of defining dose is dose to a point, and we pick a reference point. The ICRU reference point is located, chosen to represent the delivered dose. And here's some criteria. So the point should be located in a region where the dose can be calculated accurately, so not in a buildup, not in a steep gradient, or so on. Second, the point should be in the central part of the PTV, so where you're trying to treat, right here, right? And then the third point, final point, for multiple fields, the isocenter or beam intersection point, that's recommended as the ICRU reference point, unless there's some reason to do otherwise. Okay, so there are some drawbacks to specifying it this way, dose to a point, especially with IMRT, and I'm going to come back to this in a few minutes. So volumetric dose prescription is the way to go. This is what ICRU 83 is advocating. So I'm going to spend a few minutes then looking at how we do that. What are some of the metrics that we can use to specify a volumetric dose? So let me start here with a PTV, some volume you want to irradiate. And let me draw a dose cloud here. So I'm just going to draw it as a square, and that's going to be, say, 100 centigrade in this box. Then in the middle of the tumor, there's another dose. I'm going to say that's 50 centigrade. And on the other edge over here, another dose that's 10 centigrade. Okay, now let me draw a plot of this. So what I'm going to draw here is the volume on the y-axis in percent of the total volume, and then dose on the x-axis in centigrade. This is going to be a dose volume histogram, DVH. So let me go over here and mark off the doses. So 100, 50, and 10. And of course there are doses in between, I'm just not showing them. And then let me go over here and look at this. So over here, the whole tumor is covered by 10 centigrade or more, right? So 100% coverage at least that level, right? Some parts are hotter, but definitely everything gets at least that. Okay, so that's one point on this curve. If I go and look at the 50 or more line, I'm going to say something like maybe this much of the volume gets covered. We can argue about where this should be, but you do the calculation, it's maybe a half or 2/3. Okay, then let's look at the 100 line. And so how much of the volume is covered by that or more? It's this little bit over here. So let's say that's about a third, let's say, something like this. So that's another point on this DVH graph. And then I can connect all these points, and if I did calculations for points in between, that's what I'd get. And there's some hot spot too where it gets actually more than 100 and it ends up here. So that's a DVH for this coverage of this target. Let's look at another case. So let's say we had a coverage like this, where I got very uniform coverage of that 100 gray line, and then I'd have some lower isodose lines out here, say 50 and 10, and I'm not going to show the lower ones, but maybe there. So if I go out to 100 centigrade, what I see here is that the whole tumor, 100%, is covered at 100 centigrade, or at least 100 centigrade, 100 centigrade or less. So the line would come over like this, and then it would fall off. I don't have any kind of hot spots here. So this is a uniform coverage of the tumor. So uniform DVH is just kind of like a step function straight down. That's an ideal uniform distribution. Let me zoom in and redraw this a minute. So this is kind of the curve I just showed. I'm going to show you how to pull out some statistics from this. So typically it might curve down like this, let's say. Now I'm going to draw an organ at risk down below. And let's look at the low isodose lines, say 10 centigrade or even less. For those low lines, the entire OAR is going to be covered. I'm not showing those lines, they extend out, but I think you can imagine. So I got 1 point on the DVH down here, 100% coverage at low isodose lines. And now let's look at the high isodose lines. Those will be right here, right where the tumor abuts up right next to the OAR. So we're going to have some dose out here, and the volume is small, almost like it's really small here. You can see that, right? This volume of the OAR. So it's going to, at high dose, you can have a small volume in the OAR. So let's put the point down here. It's going to be almost close to 0. And then if you did the calculation for intermediate doses, you would get other values, and you could connect these, and you might get a curve that looks something like this. So this might be a typical curve for an OAR that's close to the PTV. Now let's look at how to pull out some dose statistics. So let's say in the PTV I want to find the 95% coverage line. So what dose does 95% of volume get? So I would look up on the graph like this, and then this point would be D95, 95%. All right, so that's the dose received by at least 95% of the volume. Here's an example. Let's say D95% was, let's say 4490 centigrade. This is just an example. Okay, another way to write this, D95% might be 99.58%, okay, of a goal of 4500 centigrade. So you can either write it as a dose or as a percentage in either way, but you should specify clearly. So this is typically the nomenclature, but some people will just say, for shorthand, D95, and you don't know whether they're talking about 95 gray or 95%, but the better way is to write it with all these symbols rated out. That's how TG263 says we should do it. All right, now let's look at the OAR. So maybe I wanted to look at the 30 gray dose and see what volume is covered by the 30 gray dose. I could look that up on the curve, and then I would see here the value for V30 gray. So that would be V30 gray, the volume receiving at least 30 gray. Now let's look at an example. So here we might have V30 gray is equal to, let's say, 45% of the volume of that OAR. So here are different ways to specify it. V30 gray, you could say it either in percent or in cc's. Sometimes people say just V30 for shorthand. But again, it's ambiguous because you could actually mean V30%. What's the volume at 30% of the dose prescription? So better to specify like this, and this is the nomenclature that TG263 advocates for. Spell it all out. So now I'd like to talk about one more parameter that you can use to specify dose distributions. When you look at this picture, I showed a dose that wrapped fairly tightly around the target volume. But you can imagine that in theory, I could have a very large dose cloud that didn't wrap tightly around the target volume. And yet I would have the same DVH for that target volume. And so you need to be able to distinguish those two scenarios. One plan is quite different than the other. And so the way we do that is with the conformity index. And here's what that is. The simple definition of conformity index is pretty simple. It's the ratio of the total volume receiving some prescribed dose, let's say 100%, that ratio to the volume of the planning target volume. So it's the total volume divided by the planning target volume. So you can imagine if you have a very large dose cloud that extends way beyond the PTV, this ratio becomes very large. If that target volume is equal to PTV, the value is 1. So ideally, this value is equal to 1 or close to 1. And then you'll sometimes see this number, the conformity index 95, and that's the ratio of the volume receiving 95% of the prescribed dose to the volume of the PTV. And the idea there is that sometimes the 100% line doesn't necessarily cover the tumor volume by design. And so here you can look at CI95 to try to get a value close to 1. So let's look at how this plays out in an IMRT plan. I'm going to talk about IMRT plans more in future videos, but for now let's just look at the image. And here's a head and neck plan. And what you see here is there's 3 different PTVs. One PTV in red gets 70 gray, another PTV in orange gets 65, and then the yellow PTV gets 55 gray. So what you'll see is the DVHs on the left, and you see there's different volumes, 3 different volumes, but within each volume, so like within the red volume, you can have heterogeneous dose. So you can have different doses. So you'll see there's a point here, for example, which has it's at a hot spot. And there are other points in the volume which are a little bit colder. So it's not exactly uniform within that PTV. And so there are implications of that. So let's look at that. Here's a plan I drew up with same plan, both cases, but prescribed at 2 different points. On the left, to point number 1, which happens to be in a hot spot, you prescribe 212 centigrade times 33 fractions to that point. On the right, same prescription, but to this other point here, which happens to be in a cold region. What does that do? Let's look at that in terms of the DVHs, because it will have an effect. So here what you see is the clinical plan in the solid line, actually treated. And on the right is the DVH if you were to prescribe to point number 2 in the cold spot, which makes the overall plan hotter. And then on the left, you see to the prescription to point 1, and the overall dose is a lot lower to this PTV. So you'll see that prescribing to points, especially when you're doing IMRT and there's heterogeneous doses, it's not really a reliable way to do it because it doesn't fully specify the dose that you deliver. And it can be substantial. Here's some data on this. This is a study quoted in ICRU 83. This is led by Inder Das, where they looked at prescribed doses versus planned doses in 800 patients at 5 institutions and different planning systems. So ideally what you would want is that the prescription dose matches the planned dose. So the value should be 1, the ratio should be 1 here. But you'll see that it's not. There's a lot of variability, and you'll see it can go from 50% to above 40% in the outliers. You'll see different metrics here, minimum dose, maximum, medium dose. And you'll see especially with the minimum dose, it varies a lot depending on what system you're using. The median dose, the black dots, they're a little less variable, although there is still quite a bit of variability. So the final conclusion then of these considerations, point dose prescriptions are really not adequate, and especially for IMRT plans. And that leads to the way that we should prescribe dose, and what ICRU 83 recommends: use a dose volume prescription approach, not a point dose. And they also advocate that the D50% value should be reported. That seems to be more consistent. And also any other dose to some volume which is believed to be clinically relevant, like, for example, D99, the dose to 99% of the volume or more. All right, so with that, you understand some of the very important basics of the terminology and concepts that we use in treatment planning. I'm going to leave you with a little bit of further reading here. And then in the next videos, we're going to get into the concept of plan quality. What does it mean to have a good plan? What does good mean? Okay, we'll see you in the next video.